And also, good morning, friends. Let us discuss the optical receivers. It is for optical fiber communication, as well as it is helpful for your GATE preparation, GATE 2021 exam preparation also. Let us discuss the optical receivers and their performance parameters. I want to share the material. So let us start optical receivers and their operation. Let us see. So go to the material. So let us see what is optical receiver. So what is optical receiver? The light which is traveling through the fiber at the receiver, we have to recover. We have to convert the photons which are generated, which are propagating through the fiber into the proportional electrical form. So conversion of optical into the optical proportional electrical signal is done by the photo detectors. So we have the photo detectors. Here, optical receivers. Here we are discussing about the optical receiver operation, receiver sensitivity, eye diagram, and eye diagram. Okay, just a wait. So page number 154. So optical receiver design. Let us discuss the optical receiver design. A optical receiver design is a system which converts the optical energy into the electrical signal and also amplify the signal and process it. The optical receiver system, we have the three blocks, made up of three blocks. First one is a photo detector, photo detector. Here you can see the photo detector. Then we have the second one is amplifier. Second one is a amplifier, and the third one is a signal processing circuit. Photo detector, amplifier, and signal processing circuit. Any optical receiver is made up of photo detector, amplifier, signal processing circuit. Okay, in model 3, we have the optical receiver design discussion. So any optical receiver system is very important block of any optical fiber communication network. Its work is very important because it have to convert the optical energy. Okay, in the transmitter we have the electrical signal and converted into optical photons. Okay, or photons. So these optical signal is made to propagate through the fiber, and at the receiver we are receiving the optical signal which are in a weak, which are very weak in strength. Here what we are doing in the receiver, we are converting the optical energy which is received into the proportional electrical signal. And any optical receiver is made up of photodetector. This is called as a front end. Okay, this is called as a front end. There are three blocks. This is the block. Here you can see front end, linear channel, data recovery. Okay, so optical receiver system converts the optical energy into the electrical signal. Also, we have to amplify because we are receiving very weak signal at the receiver side. So that weak signal we have to amplify. At the same time, we have to process it to recover the original electrical signal. Many noises such as short noise, thermal noise, then quantum noise, and dark current. So these are some of the noises, and also ISI effect and the intermodal distortion. These are some of the distortion or losses. Okay, these are the different noise they may present in the signal which is received at the receiver side. So these are the unwanted electrical signals. Short noise, thermal noise, Johnson noise, it is also called as Johnson noise. Then we have the dark current. Then we have the the impedance matching problems. So all are present in a optical energy. So optical energy converted into electrical energy, electrical signal. So these noises affects the signal quality. The signal quality is affected by these noises. Okay. So let us see the block diagram of any optical receiver. Then let us see the different noises which affects the optical fiber communication link. So any block of the optical receiver is made up of three blocks. First block is a photodetector. It is called a front end. Then we have the amplifier. It is also called the linear channel and signal processing circuitry. Right? It is also called the data recovery. Okay. So these are the photons, optics made to fall on the photodiode. Here we can have the pin or APD. Okay. There are two types of photodiodes, pin or avalanche photodetector. So these are made up of photodiode. On the surface of the photodiode, these are the made to fall. These are the optical signals. These are made to fall on the photodiode. The voltage control is used to control the voltage here. Then we have the pre-amplifier to amplify the weak signal which is generated. Okay. Here we have the optical signal, and at the output of the photodiode we have the electrical signal. Okay. So optical signal is converted into electrical signal. So these electrical signal which are very weak in strength. Okay. So that we are amplifying here, and the amplifier name is called as a pre-amplifier. Okay. So these block photodiode, preamplifier, voltage control, and conversion of optics into electrical is called as a front end. Okay. Then the second block is here called as a linear channel. Now here the input is electrical signal, and here we have the amplifier, and here we have the gain control, which is used to maintain the gain of the amplifier. Then here we have the filters. So these filters are used to remove the noise which are generated in the different blocks here. The photodiode also generates some noise. Voltage control, amplifier also we know different many noises are present in the amplifier circuit also. So these noises are here. So these noises are removed by using a suitable filter. Okay, suitable filter is used. So these filters are here. Then the third block is called as a data recovery block. Okay, and data recovery block, here we have the decision circuit and the clock recovery. We have to sync the input with the output. Okay, the transmitter time and the receiver time both have to be synced. So that is why the clock recovery and the decision circuit, and at the finally we are getting here the data output. So the front end, linear channel and data recovery. This makes the optical receiver design. Okay, here you can see a very important point. Noise generated in receiver must be controlled precisely as it decides the lowest signal level that can be detected. Lowest level signal. Okay, the noise is more means the detected signal is the also lowest. Okay, minimum, lowest or minimum, which decides. Okay, then noise consideration is an important factor in the receiver design compared to the transmitter. The noise consideration is very important here. Okay, that will affect the overall optical receiver operation or a signal, simply the signal quality. Okay, will be affected. Another important criteria is a optical receiver is a average error probability. Okay, it is also called as a bit error probability, BER. The parameter is called as a bit error probability. Number of photons sent and number of photons are corrupted. If you are sending 100, then what are the chances of the error probability? Out of 100, 20 are corrupted. So that 20 is a 20% is a corruption rate. That is called the bit error probability. The probability rate of corruption of the bits. So that parameter is given with the bit error probability. Bit error rate. It is also called the bit error rate. So let us see the equivalent circuit of the receiver configuration. So already I was explained, it is made up of three parts. So first one is here you can see the front end. Then we have the linear channel. It is made up of amplifier. Then the gain control. Then we have the filter. And the third block is a data recovery. Same thing we are drawing here. That is called the equivalent circuit. So it is also called the optical receiver configuration. Okay, remember this is the optical receiver configuration. Okay, so here the first part again we have the detectors, photo detectors. Here we have the photo detector capacitor. Then we have the RB. It is a bias resistor. Okay, RB is a bias resistor. CD is the capacitance of the detector. And this is the photo detector. Okay, this diode is nothing but the photo detector made up of either pin or APD. Pin or APD. PFT is a power of optical energy. Power of optical signal that is given by the power. So P of T. Okay, so this is the photon. Okay, the arrow is shown as a photon. It is made to fall on this photo detector. So this photo detector at the output generates here the electrical signal. Okay, electrical signal is generated at the output of the photo detector. Okay, so the here we have the capacitance. This is a biasing RB, not the RB. So because of this bias resistor RB, IB of T. Okay, this is called as a IB of T. So this IB of T is nothing but a current. I stands for current. B. Okay, this is a because of the bias resistor, a current is flowing that is of thermal. Okay, this is one of the thermal noise. Okay, this is the one of the thermal noise. Thermal noise. Okay, so that is because this thermal noise current is because of the bias resistor RB. Okay, so here you can see the dashed line. So this is the for front end. Here we have the linear channel, the amplifier. So here again RA CA, the combination. You can see the RA and CA both are in a parallel, connected in a parallel. RA is a amplifier resistor, CA is amplifier capacitor. Because of this, again, a thermal current, thermal noise, because of the current is flowing. So this arrow shows IA of T. Okay, so IA, A is for because of this resistor. Okay, resistor of the amplifier. A current is flowing, and this current is a thermal current, thermal noise. Okay, this is the current, which is, and this current is nothing but the thermal noise. Okay, and here we have the impedance. As amplifier we know we have the impedance. Then here we can see EA, small EA, EAT T. This is the voltage generated. Okay, and here we have the amplifier, and this is the equalizer. And finally, we are getting the V out output. Okay, current is converted into voltage. Up to here, we have the current, and the current is converted into voltage, and V out is a voltage output. Let us see in detail the different parameters of the photodetector parameters and the amplifier parameters. So photodetector parameters, either we have the pin or APD, and the different parameters are of the photodetectors are gain. So gain is given by the M. So M is equal to 1. Always we have to maintain the gain which is equal to 1. Then the quantum efficiency is given by here. Already we discussed about the output to input, number of photons generated to number of electron hole pair injected. Or for this, number of electron hole pair generated to number of photons incident. So that is a quantum efficiency. Okay, number of electron hole pair generated to the number of photons incident. So that is a ratio, that is a quantum efficiency. Then we have the capacitance CD, bias resistance RB, and the thermal noise current. Already I have explained about this, generated by bias resistor RB. Then we have the amplifier parameters. So the parameters related to the amplifiers are input impedance RA, shunt input capacitance CA, it is CA. Then we have the one more parameter called as transconductance. So that is a I by V. Transconductance given by the GM. Okay, GM. It is a parameter or ratio of current to voltage, amperes to voltage. So this is the transconductance is a parameter of the amplifier. Then input noise current, because of the this RA, amplifier resistance, input noise current IAT, because of thermal noise of the RA, thermal noise. Because of thermal noise, we are generating the current, and that current is a IA of T. Okay, and this is called the input noise current. Okay, here also you can see the thermal noise current. This is the thermal, this is also the thermal. Okay, IA, IB. So these IB and IA are the currents called the input noise currents because of the thermal noise of the RB and RA respectively. Then finally we have the equalizer. So this is the equalizer, you can see here, this is the equalizer. So equalizer is used to get the shaping of the signal, a perfect shape we have to get at the output. Then the ISI and the signal distortion had to be removed. So the ISI effect, inter-symbol interference. ISI stands for inter-symbol interference and signal distortion. These two effects have to be nullified. Okay, have to be nullified. Okay, nullified means we have to remove it and also give the a perfect shape of the V out. So that is the use of this equalizer. Current to voltage. Okay, here we have the current at the output of the amplifier. Here we have the current and output is V out. So current to voltage conversion and removing of ISI, removing of ISI and in other distortions have to be removed. So this is done by using this the block called the equalizer. Is it clear? So these are the receiver configuration and different parameters related to the optical receiver. Okay. So we discussed about these current, thermal current here, thermal current, and this is the voltage, noise voltage. Here we have the noise voltage. Okay, and P of T. Okay, then let us see the expression of the mean output current of the photo output current from the photodiode. Let us see what are the assumptions. They have made three assumptions. All noise sources are Gaussian in statistics. These are the assumptions. Second one, all noise sources are flat in spectrum. Okay, and third one, all noise sources are uncorrelated, means they are independent, not related with each other. We have the noise here. Here you can see the input noise current IA. Then here we have the current. One of the noise called as IB. So these noise thermal noise of the IB and the IA both are independent. They are not related with each other. So that is the meaning. So these three assumptions are made. All noise sources are Gaussian in statistics. Noise sources are flat in spectrum. Flat. Okay, means there is no fluctuation. Fluctuate. They are flat, and all noise sources are uncorrelated. Means they are independent. Okay. So this is the equation: binary digital pulse train incident on photo detector. Binary digital pulse train. Here you can observe the train. Train means we are getting one by one. Okay, at the surface of the detector. Here you can see the detector. Okay, continuously there is a incident of photons on the photo detector. Here you can see the photo detector, and here these pulse. You are getting the pulses incident on the photo detector continuously. Then it is called as a train, pulse train. The equation is here. So that is P of T. Okay, P of T. Then we have the Bn. Here we have the HP bracket T minus N T B. Okay, where P of T is, here you can say received optical power. This is the power. Then TB is the bit period. This is the TB is a bit period. Bn nth message bit. Then HP received pulse shape. Here we have the HP which decides the shape of the pulse. So at time t, for a particular time t, the mean output current due to the pulse train PFT is given by at the time, a particular time you are selecting here. For that particular time, what will be the mean output current? How much current is generated due to the pulse train PFT? Okay, are you getting? PFT is a optical power. PFT is a optical power. Because of this optical power incident on a particular time on a photo detector, how much current is generated at the output of the photo detector. Okay, so that is given by this equation. So I of t, I is the current at a particular time interval. How much current is generated at the output? That is given by N Q by HV M P of t. Are you getting? So this is nothing but the responsivity. Please recall in model 2, we have discussed about the responsivity. Okay, or not. Please remember, we have discussed about the responsivity while discussing the photo detectors. So this equation is nothing but responsivity or not. Okay, this is the or not, this equation. I will show. This is nothing but the or not responsivity. Okay, so this is the responsivity. Please recall N Q and HV. Okay, remember here this is the quantum efficiency. This is electronic charge Q. Then H is a Planck's constant, and V is nothing but what? V is nothing but the frequency, and this is the M. Okay, M is nothing but the gain. Already I have explained here. Here you can see the gain. Gain equal to 1. Then P of T. This is the P of T. This is the P of T. Okay, this is the P of T. So here you can see the M is gain of photo detector. Okay, so this is a response of photo detector given by the R naught. Here, if you neglect the dark current, already told the dark current is nothing but a noise, type of the noise, which is because of when there is no incident of optical pulses on the photo detector, and there is a generation of a small current. A small current is generated on the in the circuit when there is no incident of photons are getting, then a small amount of current is flowing, so that current is called the dark current. If you neglect this dark current, the mean output current, I already explained, the total current in a photo detector is sum of the current which is generated after the conversion of the photon into the current plus dark current. And the current, dark current is nothing but the current is generated when there is no incident of the photon. So that is a total current. Here we are neglecting this dark current. Instead of this equation, we are entering here R dot, then M, then this equation. Okay, this equation sum of n minus infinity to infinity Bn. So this is nothing but P of t. Okay, here we have the P of t. This P of t, here we are inserting, instead of the P of t, the equivalent of P of t is here. Okay, and M is the gain, and this is the responsibility. So this is the current of the output current of the receiver. Okay, so we don't have the syllabus in the preamplifiers. So I'm neglecting this preamplifier. So directly coming to the different noises. So this is the bandwidth. So bandwidth is given by this equation. Just go through this bandwidth equation. This is the bandwidth. Then we don't have these. Okay. Receiver noise. Directly coming to the receiver noise. Here we can see the receiver noise. Receiver noise is because of, already I explained, the noise is generated by the spontaneous fluctuation of the current and voltage. And different noises are short noise, thermal noise. Okay, when photon incident on the photo detector are random, okay, are random in nature. The quantum noise, okay, or short noise is generated. How the quantum noise or short noise is generated? When the photo detector, the incident of photon on the photo detectors are random in nature. Okay, and because of the random in nature, the incident of photon, we are generating the quantum noise. Or the quantum noise are short noise. Okay, there are two types of noises. One noise is internally generated and another one is externally generated to the system. Here only we are considering about the internal source of noises. In our discussion, we are considering only internal source of noises. And in a receiver system, the error arises because of the noises and disturbances in the signal detection system. Here you can see the noise is a unwanted electrical signal. Unwanted electrical signal. Okay. The other sources of photo detector noise are dark current. Already explained about the dark current and leakage current. With this, we have the symbol interference. So here you can see one of the effects called as the pulse spreading. The energies are distributed in a adjoining or neighboring pulses or slot. So this is called as a pulse spreading. Okay, it has to be present in between these two. This is the perfect shape of the signal. But as the pulse travels in a optical fiber, there are chances of the spreading of the pulses and the energy is spread in a adjoining slots. Because of that, the energy is lost here. So that is given by here, received signal level and the time. Okay, this is the time. So noise mechanism, okay, V out. Okay, here you can see the V out. So total voltage output is sum of voltage output plus total noise. Okay, so this is a noise voltage. Vn of T is a noise voltage. V on T is a noise voltage. Mean output voltage. V out. Here you can see the V out. So total output voltage is sum of output mean output voltage plus noise voltage. Okay, this is the mean output voltage plus noise voltage. So this is the total output voltage generated. So what is this noise voltage? Okay, so noise voltage again can be expressed as short noise. Then here you can see the VR, V short. Then thermal noise or Johnson noise. This is the VR. Then the amplifier input noise current, because of IFT, we are getting the voltage IA of T. Already I explained, because of this bias resistor, we are getting the thermal noise called as IA of T. Because of IAT, we are getting the voltage noise called as VI of T. So here you can see the V of T. Then we have the VE. VE. This is the resulted by amplifier input voltage IA EA of T. Here you can refer this figure EA of T. Here we have the EA of T. Okay, here you can see the EA of T. So because of this EA of T, we are getting that voltage. Okay, so this is the total noise voltage of a optical receiver. So one by one, what is short noise or thermal noise? Go through this. These are the equations of these. Again, in detail, what is this? And this equation is given by and VI, then VE. Okay, so this is given by VR, 4K BT, Boltzmann constant RB. Okay, so this is the equation. Then the VE given by this equation. V short noise is given by this equation. Please remember these equations directly. There is no derivation. Directly we are writing here. So just remember these equations. So total here you can see here in this table. You can summarize all the noise voltages like this. Okay. So receiver sensitivity, to calculate optical receiver sensitivity, total noise in the receiver is calculated. Total noise. Okay. So here, substitute these values in the following equation. The mean square input noise current is given as similar to the voltage. We have the input noise current also. So how the noise current, input noise current, okay, it is also given by IS square, IR square, I1 square, IE square. Okay, this is the short noise, then thermal noise, shunt noise, series noise, then the total noise. If you substitute all these equations in the above this equation, you will get the mean square input noise current of the optical receiver. Okay, here we have put it all the equations. So this is the thermal noise, shunt noise, series noise, and the total noise. Here this is the total noise. So remember this total noise present in a optical receiver. So this is the example. Go through this example. In a indium gallium arsenide pin photodiode has a following parameter at a wavelength of the 1300 nanometer, dark current 4 nanoamperes, quantum efficiency 0.9, RL load resistor 100 ohms. Okay, and the leakage current is negligible. The incident optical power is 300 nanowatts. If you convert into dBm, minus 35. So find the various noise terms of the receiver. Okay, these are the parameters given. So solution put here in this equation. So mean dark current given by this, mean square thermal noise current IT square given by this equation. So where V is a Boltzmann constant, if you substitute here, so 3.28 into 10 to the power of minus 16 amperes. Okay, so here in this discussion we have discussed about the optical receiver, different blocks of the optical receiver, then the configuration of the optical receiver, and its equivalent circuit, different mechanism, what are the noises present, okay, different parameters we have discussed. Okay, then the voltage, noise, voltages and the noise currents. So different equations we have seen for the short noise, thermal noise, what is ISI effect and the intermodal dispersion. Okay, so let us stop here and next class let us discuss the optical receivers, some more problems let us solve. Okay, so these are regarding the optical receivers. Okay.